Welcome everybody to the Streamlined Efficiency Unshackling Kubernetes Image Volumes for Rapid AI Model and Dataset Loading presentation. Today we're going to talk a little bit about how we can go about speeding up volume loading when using image volume specifically. So to start us off, I'm Esteban. I am a software engineer from Microsoft. I specifically work on Azure Container Registry. One second. Um, My main area of expertise is OCI conformance as well as artifact streaming. My co-presenter over there is Yifan Yuan from AlibabaCloud. He's a senior software engineer there and a researcher who's done many contributions to the Overlay BD project. So to start us off, I want to speak about the current state of efficiency when it comes to starting up images and how we can deal with accelerating those. So the first thing to note is that today we have achieved a lot of progress on image startup. The first thing is we have artifact streaming. However, artifact streaming helps us solve one problem, which is how do we optimize workloads that are specifically application based. But when we start to deal with, we need to have these large data sets along with this, we start to encounter some problems. Packaging our information into our current images and then streaming them is not necessarily efficient. We want to be able to load data at a scale, but at the same time, we don't want to necessarily pay the upfront cost of packaging this data and putting it in our container registries. So when we're dealing with large language model training or just AI in general, we sometimes need to load data in parallel. This data parallelism presents a lot of challenges and means that we actually need to be able to simultaneously access lots of data across multiple places at the same time. This presents a number of challenges. The first of which is we need to be able to have data that can be accessible all the time. So if we don't have continuous data access, we're going to end up paying a lot of money for GPUs that are not in use. We're going to be unable to actually load all the data when we need it, as we need it. We also need to make sure that when we do access the data, it's actually fast to access. Additionally, because we're dealing with Kubernetes clusters, we obviously need to be able to scale up our access. If we're not able to scale up to thousands of nodes, then we're not going to be able to use this data effectively when training AI models or any other thing that requires large data sets. And finally, there are some things about management that we really need to think about. First of all, this data is likely to need to be versioned. So we need to have versioning that matches both the data and the application side. Finally, but most important of all, managing this data needs to be easy. We cannot have any applications that are too difficult to manage because nobody's going to use them. So given that we have these challenges, we need to consider that we do have a lot of solutions for this. So here's where image volumes come in from OCI. So when we're talking about OCI registries, we already have a lot of these challenges tackled. First of all, OCI registries need to be performant because they already need to scale up for these Kubernetes workloads. They already need to be highly accessible, highly available, and in general, people are somewhat familiar with them. So we also know that they solve a lot of the versioning problems. We have tags for versioning, as well as digests and manifests. So specifically, tags can give us the ability to have arbitrary definitions for our different images, right? So any data that we have, we could version this way. We also get the benefit of using digests within our manifests to actually maintain data consistency and also have versions that will not change over time. Beyond all of this, there is one other great benefit that we get from having our data in OCI registries. We can enable garbage collection for this. Now, this is very important because every year data keeps growing and growing and it's out of control. Nowadays, there's been some studies, including an IDC report, that tells us that the total data in the world will grow by 175 zettabytes by 2025. And if you're an organization who needs to have these very large data sets that are versioned as well, you're going to keep using lots of data. And if you're never able to clean that up because you don't know what sort of runtime it's tied to, then you're just going to end up accumulating costs with no end in sight. So I mentioned this a little bit before, but users are already familiar with OCI registries. The distribution spec is well known and well defined. And in general, people have to use it for Kubernetes. Of course, tooling is always wonderful. So being part of the ecosystem means that if we can actually leverage the registry to also tackle this particular challenge of loading large data sets, then we can get a lot of advantages. Now, has this been done before? To some extent. There's actually a long history of using OCI images to store arbitrary data. The ORAS project, for example, formalized this at some point by defining how you can put any sort of arbitrary data into an OCI artifact. We also have image volumes, of course, as the presentation has been talking about, which allow you to actually load container images into a file system in the Kubernetes side of things. Okay. There are some questions why we might need to hold off on doing this sort of thing. So the first thing is that registries were not designed initially for volume mounting. What this means is that there are some things that don't necessarily work out of the box, or at least not across all registries. For example, we need to account for the fact that different registries tend to have different size limitations. For example, the ACI registry has somewhere around the 200 gigabyte limit per layer. But this is not consistent and is not specified in the OCI distribution spec, so it varies depending on implementation. The other thing is that while we have been able to get streaming support working on container registries, this was not something that was built into the spec initially. Now, there are some things that allowed for it to happen today, but originally was not built for this. So it's not something that we can say was intended from the start. The other thing is that there are some limitations when it comes to how we store the data inside of images that go into registries. OCI registries tend to store information using a overlay file system, which is a union file system that basically creates new layers every time you modify the data. So if you're dealing with a very large data set, a very large data set that might be changing at any point, this means that you might need to actually constantly build new layers, and eventually you're going to run into some layer limits, and there are costs to this sort of overlay structure. This means as well that every time you're adding new data, or even at the first time you're doing this, you need to package a lot of this data. And as we'll see in a moment, packaging can be quite expensive. So here is a bit of an illustration of what the cost is for packaging a bunch of data. So we grabbed some data sets from kaggle.com. We grabbed some popular machine learning training data sets just to get a little bit of an understanding of what the cost is. We used copy from Docker using a Docker a Docker file, and just to try to illustrate this so people can replicate it if they want to. And then we started packaging these, and we noticed a number of things. First of all, as you have more files and generally larger images, you tend to have much, much larger times to package. For example, the largest data set that we had in this case actually took almost 4 hours to package, and it's only 22 gigabytes. In the modern world, 22 gigabytes is not that much, but for the purposes of images, it can be quite a bit. I mean, I do want to note that this particular dataset does have something like 700,000 files, and they're mostly images, so they're not very compressible as well. There's some considerations there, but nonetheless, Even the smaller data sets, in the order of just a few gigabytes, would take many minutes to actually package. So we can start to see that this is something that is maybe not ideal. So from here on, we've noticed that we've already solved a lot of the problems, but we have something to consider. So the registries provide high availability and scalability and performance. We have some measure of versioning data, and we can support data garbage collection natively. They're also widely adopted, in use across a number of tooling, and in general, they are something that most people will already be familiar with. So that said, how can we solve that biggest challenge for us, which is packaging, so we can actually use this for larger data set loading in AI workloads? So now my colleague Yifan will introduce what we've actually done to fix this issue. Yifan?
Okay, thanks Esteban for his speech. Now I will show you how to solve the problem raised earlier. Uh, the inspiration for this came from the indexing to OCR image. Uh, the community already has some solutions that a remote snapshotter can create a mount point for streaming by external indexes and without repackaging the image, such like the Sequable OCI Sochi and Overlay BD. The core of these solutions is they can uh, package an index file of the image layer content and their own metadata by hooking the I/O request at the file system level or block level. Um, it combined with the image index, they can find the corresponding data for the remote image. So, taking a bold speculation, could we build an index for the entire storage bucket? My answer is yes. I'd like to introduce you the e-link. That solution can create a mount point for accessing remote data through OCI artifact and no need to package them. The dataset description, reference list, and remote snapshotters are the core of this solution. Uh, Reference list is a set of data objects you want to package into the OCI artifact. Remote snapshot here will pass the reference items from the reference list and create the mount point for streaming. More details, reference list contains a set of records. Each record has at least 4 parts. The source path is the original path uh, for the object in the remote storage. The mount path, the path when you access the object from the mount point. E tag, E tag reflects the data changes and it represents a version of the object. People can know whether the data has been changed from the E tag instead of downloading it. And file size, the object size in byte. Through the reference list, we can describe all the objects we want to access within an OCI artifact. Now let's package the reference list into an OCI artifact. First of all, we need a registry to take over the backend storage, which enable us to get the target blob URL from the registry. As we all know, when we try to get a blob from the registry API, the registry will return either a redirect URL or the blob content, depending on the status code. So it's easy to get the backend storage endpoint from the registry API and combine with the source path field, we can get the actual path of the target blob. Second, a special annotation field is needed. This can uh, identify that the current layer is a reference list, which can conveniently enable the snapshotter to support accessing remote files for the existing OCI artifact. Of course, there may be better approaches in the future. And also, the reference list should be saved as a common format like CSV or JSON or something else, so that the registry can analyze the details of the reference list to get the valid data across the entire storage bucket. When we create a e-link command point, the container runtimes should pull and unpack the reference list through the regular image pooling process. And the snapshotter will create the mount point by parsing the reference items. Yeah, snapshotter should create a file entry. Create a file entry at the relative path of the mount point according to the mount path field. And this file entry actually point to its source path. Please note that the access permission is required here because the registry may not have the access permission for all the remote objects. So an additional authorization may be needed. Streaming loading enables the container runtime to mount the image volume without pooling. It skips the downloading process of the artifact. And more important, when the dataset is too large, it will occupy a lot of storage space and even failed to download it. So the streaming loading is essential here. When the streaming service handle an I/O request, it should convert the I/O request to the uh, corresponding data of the reference list. After ensuring that the E tag has not been changed, it converts the I/O request into a range get for the remote target. For the proof of concept, we choose overlay BD. Overlay BD provides a merged view of image layers as a virtual block device. It supports on-demand transfer data as disk sector level, and it also provides a mount point via a block device interface rather than fuse, which has a better performance in the small files accessing and more mature in handling the stability problems like crash recovery. The most important is overlay BD has been widely used in the production environment of Azure and Alibaba Group and Databricks. Overlay BD has a lightweight mode called Turbo OCI. It already supports indexing to OCI image, and also it can build ext4 EROFS file system meta from image index locally. To support E-Link, we can just implement a simple function to map the I/O request into reference list. Since overlay BD provides a backend implementation of a block device, the I/O request from the mount point will be converted into a simple read and write operations through the file system and block driver. That is also one of the important reasons why we choose OLBD. Based on the plan above, we conducted performance tests on E-Link for packaging and full volume access. During the packaging phase, E-Link transformed the file copy into recording the reference data, which gives E-Link significant advantages in both packaging time and build speed. For the 22 GB dataset, which contains more than 700,000 files, the packaging of OCI image takes nearly 4 hours, but E-Link build speed is less than 2 minutes. At last, we tested the E2E data access performance. This chart compares the throughput of traditional OCI images, Goofies, and E-Link. Goofies is a high-performance implementation of AWS S3 file system. The right axis of this chart shows the average size of individual files in each dataset. In this test, we add the preparation time. The preparation time for OCI image include the downloading and unpackaging, which is the default behavior for creating an OCI volume mount point. For Goofies and E-Link, the preparation time is include the time taken to create a mount point and build the file system metadata. The result shows that in the scenario with a large number of small files, E-Link performs significantly better than OCI image and Goofies. In the US accident dataset, with a large single file, E-Link performance is also on par with Goofies. And all the test environments were provided by AlibabaCloud. Let's conclude our presentation. Thank you for listening and welcome any questions.
Thanks for the presentation. I just had a couple of questions. One is, how does this work with six-door image signing? And second, when you are streaming a blob, how do you verify the checksum on the target host? Thanks.
You want to handle that one? So I don't think we're yet at the stage where we're doing a lot of security verification for some of these things. We are doing verification using the E tags to at least validate that the contents that we're requesting are actually what we want to get. This is still somewhat early stages, so I don't think we've gotten quite there. As for streaming purposes, do you know what kind of validation we do there?
Oh, we have to check some. We have to check some for the Z file to verify the data is correct.
Yeah, I just want to know, when you are streaming, if you get the entirety of the data, how do you verify the checksum?
Yeah, he's asking how do we verify the checksum if you haven't gotten all of the data?
We just check the E-Link. E-Link is the MD5 checksum of the object. Maybe sometimes. Before we get the data, we through HTTP head response can get the E tag. And the E tag is also saved in the reference list. If the E tag is mismatched, so the data has been changed.
Okay,
Right?
thanks.